So the last video we started to introduce the topic of impulse. Today we're talking about momentum. So momentum is the effort required to change the velocity of an object. So momentum is mass times the velocity of my object that I'm trying to change, and the units of mass are kilograms, the unit of velocity is meters per second, so the units of momentum are kilograms per meters per second. So two objects can have different masses, but they can have the same momentum. For example, you can have an elephant with a very large mass moving very slowly, or you can have a bullet that has a very small mass but is moving very quickly. Both would be hard to change the velocity because they have a high momentum. So momentum, when we're talking about that effort, a low momentum is easy to change velocity, high momentum is difficult to change velocity. So that brings us to the idea of impulse and momentum. So we know that force is equal to mass times acceleration. And we know that acceleration is delta v over delta t. So I can rewrite F is equal to ma as S is equal to m times delta v over delta t. And then if I multiply both sides by delta t, I get F delta t is equal to m delta v. So you'll recognize this F delta t as the impulse from our last video and momentum which we just covered. So impulse and momentum are related to one another. If the momentum is high, either because the velocity change is very high, then a large velocity has to be applied over a short time, or a small force has to be applied over a long time. So think about a car. If I want to change the velocity a lot, I can either really gun the engine and apply a lot of force to it in order to accelerate it from 0 to 60 in 6 seconds, or I can gently press on the accelerator and apply the force over a longer period of time to have a gentler acceleration, or any combination thereof. So how do we use this? In our first example, we have a car that has a mass of 2,000 kilograms and a velocity of 30 meters per second. So our first question is, how much momentum does a car have right now? And what is the impulse of that car? Then if I'm trying to change that momentum, how much force is going to be needed? So the first thing about what the momentum is, this is not change in momentum. It's like right now, what is my change in momentum? That would be mass times velocity, which is 2,000 times 30. And that equals 60,000 kilogram meters per second. That value is the same for the impulse, but because the units of impulse are force times time, or Newton seconds, I have to change the unit. So notice that whenever we're talking about momentum, we have to use kilograms times meters per second, and whenever we talk about impulse, we have to say Newton seconds. Well, impulse is also the change in impulse. How much effort it would take is going to be how much force I have to apply to that impulse over how much time. So 60,000 is my impulse, and I'm trying to apply it for 40 seconds. My force is going to be 1,500 newtons. That's actually going to be a negative 1,500 newtons. So let's figure out why. So let's look at that a little bit more closely by first looking at my change in momentum, right? So at the beginning, when we said, what's the momentum? That's sort of like, as it's going right now, what's my mass times velocity? The change in momentum is, it was at 60,000, now I want to take it to 0, right? So I want to take it to a stop, and my final momentum is going to be 0. My initial momentum was 60,000, or I can say m times delta v, my final velocity is 0, minus 30 was my initial velocity. So my change in momentum is going to be negative 60,000 kilogram meters per second. So let me just reiterate. When I'm just talking about the momentum a car has, right? It's not changing velocity at all. What's the momentum right now? You just multiply the mass times the velocity. Right? If it's going forward, the velocity will be positive. If it's going backwards, the velocity will be negative. If I'm looking for my change in momentum, which is what C is looking for, then what I have to do is I have to multiply my mass times the change in velocity. And because I'm going from a positive velocity to rest, my change in velocity is going to be negative, and as a result, my momentum will be negative, right? The other way that we're looking at it is my change in velocity. So my final velocity, as we said, was 0, so my final momentum is going to be 0. And my initial momentum, which we calculated in part A, is 60,000. So 0 minus 60,000 is going to be equal to negative 60,000. And pay attention to the units, kilogram meters per second. So my momentum at A was positive because the car is just cruising along. But C, because I'm looking for the change, I want to see how much I'm going to have to change the momentum to get it to stop. That's going to require delta V. Example 2. Compare the force required to cause a 2,000 kilogram car to go from 30 meters per second to 0 meters per second. And the two different scenarios are, I do it in 20 seconds, gentle braking, or I accomplish that in 2 seconds by slamming on the brakes. So instinctively, you have a sense that if I slam on the brakes, I'm going to be applying a greater force. So let's look to see if that pans out. So my change in momentum is going to be m delta v, which is going to be 2,000 times 0 minus 30. And at the bottom, I have to do change in t because I'm actually applying it over 20 seconds or 2 seconds, right? So I have a change in t. So I put my two equations together. So change in momentum is equal to change in impulse. I am isolating for my f because that's what I'm looking for. So I divide both sides by delta t. And so now I just plug in my values. 2,000 times v final minus v initial over t final minus t initial gives me negative 60,000 over 20, or negative 3,000 newtons, right? It makes sense because if the car is going forward, my force is going to have to be applied in the opposite direction. So if my car is going forward, my force is being applied in the negative direction. Well, let's compare that to the situation in which instead of braking in 20 seconds, I'm braking in 2 seconds. So I go through the same thing. M delta V is equal to F delta T. I isolate for force. But in this case, even though my numerator is the same, my denominator is much smaller. So my change in time is 2 minus 0 seconds, or 2 seconds. So now my force required is going to be negative 60,000 over 2, or negative 30,000 newtons. Right? So if I'm braking in a lot less time, the force required to stop that is going to be a lot higher. That's really hard on the body, right? So one of the things that safety features try to do is to try and increase the amount of time that our body has to stop in any sort of crash. So airbags are squishy, right? So as I'm going through it, I'm pushing into the airbag and it takes a little bit longer for me to stop. Bumpers on cars, right? Those are also going to crumple, and so it's going to take a little bit longer in order to stop the car. And all of those features are there so that when you are making me stop in a crash, which is the worst case scenario, right? That there are safety features designed to increase the amount of time that I'm changing my momentum so that the force that's applied to the body is less and you do less damage to your body, right? So imagine if you didn't have airbags and you're going forward and you weren't wearing your seatbelt. If you're going forward at, let's just use miles per hour because you understand that, 60 miles per hour, you're in a crash, you hit the steering wheel stops you in a really, really small amount of time. That's enough to break bones in your body and cause harm to your heart because the steering wheel is right at your heart, right? With the airbag has saved so many lives because what happens is it opens up and you push into the airbag, and so all of a sudden it's not the force of the steering wheel that's stopping you. You're pushing into the airbag and it's allowing your body more time to stop, and so a lot less damage. You don't have broken bones. People are walking away from car crashes in which they normally would have died if they didn't have an airbag. This is also why when you jump down, you bend your legs, or if you're jumping down from a high height and you're a stunt person, you're not only going to bend your legs when you come down, you're also going to roll because you're giving your body more time to come to a complete stop. So the force that's applied on your joints is going to be a lot less. Right? So these are all things that we tend to do naturally without thinking of it, because that one time where you jump down with very stiff legs, it hurts so much that you don't do that again. The final example is if I'm looking at the opposite. So I'm looking at the impulse and I want to see how much my momentum can change. So this is comparing final velocities. If a constant force of 8 newtons is applied to a 0.5 kilogram ball for 1 second or 2.5 seconds. Now in both cases, we are assuming that the ball is at rest, and I just want to see how fast it is after I've applied that force. So F delta T is equal to M delta V. Right now I'm solving for my delta V. So I divide both sides by M, and I get F delta V over M is equal to VF minus VI. So I solve for VF because I'm looking for my final velocity, and I get VF is equal to F delta T over M plus VI. And then I plug in my numbers. And I find that if I apply my force for 1 second, the final velocity on my 0.5 kilogram ball is going to be 16 meters per second. If, however, I apply that force for 2.5 seconds, right, so my delta T, same thing, I'm isolating for the same value, but now my time goes from 1 second to 2.5 seconds, that my final velocity is now 40 meters per second. So it's a lot higher. This is what coaches are talking about when they're talking about follow through, right? So if you are someone who is trying to accelerate a ball forward, whether it's a soccer ball or a field hockey ball, a golf ball, tennis ball, any of those things, or a hockey puck, anything in which you're trying to get that object through as quickly as possible, one of the things that they always say is to follow through so that you don't, if the ball's coming in here, you don't just sort of like clunk it like that, but you hit it and then you connect the bat and you continue to follow through. Or you have your stick, your hockey stick, and you continue to follow through so that your stick is in contact with that ball or that puck for a much longer period of time. Or your foot is in contact, you follow through. Or if you're a boxer, you follow through with your punch. Or if you're a karate person and you're trying to chop a block of wood, you follow through with that punch. You don't just sort of stop it right at that board. Then the reason is because as you're applying that force over a longer period of time, the impulse that you're creating is a lot larger. And if you're trying to accelerate a puck or a ball or anything, that contact time, even 2.5 seconds over 1 second, is enough to cause that velocity of that ball to be much, much higher. So this 40 meter per second ball is much more likely to make it over the backfield fence, or this 40 meter per second ice hockey puck is going to be much more likely to make it past the defenders into the net than something that's sort of dribbling through at 16 meters per second. So that follow through, your coaches are always talking about that, is really about good physics more than anything else.